Yeah, it's me again. And zkVMs again, more like zkVM Summit. My name is Leo. I'm working on Powder at the moment, and it's going to be a short talk about what it is. So what exactly is a zkVM? So the context here is verifiable computation. So the zk in zkVM stands for zero knowledge, but not a lot of the zkVMs actually provide native zero knowledge. What we actually want to do is a succinct way to prove that you ran some computation over some data or some program, and that you want to take this proof and then you want to convince other people that you actually ran it correctly, and that person is convinced. So before, what we used to have is zk circuits, which usually have a fixed size, a fixed length, and a fixed business logic, and then you give it some data, it gives you a proof back. And examples of this type of circuits are circuits written in Circom and Zircuities, for instance, and tons of other zk DSLs as well. What does a zkVM do? It's also a circuit, but that actually executes a dynamic program usually that comes from the input as well. So the input now is not only data that you're running computation over, but also a program. So you're going to run a given program over some given data and then get a proof for that, and the other person will hopefully be verified that his computation was done correctly. Why do we care about zkVMs? Because it basically scales proofs to any program that runs inside that VM. So we don't have to write circuits anymore for every single custom piece of business logic we want to write. We can just write programs in usually higher level language that compiles to that VM, and then we have the single circuit, which is the zkVM that runs these programs then. And there's a lot of existing zkVMs, and the past 2 years especially saw a lot of new VMs using different paradigms. And most of the current zkVMs are VM specific, meaning that they have a fixed set of instructions, a fixed ISA, and mostly direct implementations. And so we have a lot of EVM implementations actually. We have RISC-V, we have some more zk-friendly VMs that are not necessarily using more established VMs that are non-zk, LLVM, WASM, and so on. There's some trade-offs between implementing a custom zkVM versus being more flexible, which is the advantage. You probably got a lot of performance over that because you're just closer to the bare metal, and you can manipulate things a lot more like we used to do in assembly. And of course, it's what's available right now. So of course, we're going to use that. Some disadvantages of such approach is that it just becomes harder to audit, harder to change, harder to innovate on. Requires usually a bigger team to develop it, to maintain it, to think about it. And a lot of these systems are proof system specific, talking about the zk prover in the back end, and they also become hard to reuse. There's a lot of vendor lock-in and this kind of thing. So before I explain exactly what Powder is, this is the idea. So if we think about 20 years ago, 30 years ago, if you think about the gaming industry, it used to be the case that when you wrote a program, when you wrote a game, you had to write for that specific platform, Atari or some arcade system. So you basically had to port and rewrite your system for every single platform you wanted to support. And this evolved to a point where we use very nice high-level languages, and we don't have to think about that anymore as much. We still have to think about it sometimes, especially if you're developing systems, but it's way better than before. And this is basically what we're aiming at when developing Powder, is that you can write programs using a high-level language, or actually any language you want, that actually compiles to a VM that is written in the Powder assembly language. You can think of LLVM as an example, where you have many different front ends, a single compiler pipeline with multiple languages, an IR and a low-level constraint language, and single optimizers and static analysis, security passes. And then at the end, you go again to multiple backends, which here are the proof systems. And in the LLVM case, for example, would be different platforms, x86, RISC-V, and so on. But what exactly is Powder? So Powder is a compiler stack. It's basically a compiler. One word is compiler. It's a compiler stack that defines zkVMs and low-level coprocessors. So instead of writing a specific VM that has a fixed instruction set, Powder is not a VM. It's a compiler and language where you can define any VM you want. And it just abstracts away all the details of specific circuit writing for VMs and allows you to do different optimizations. Allows for modular machines, which also helps with development and security auditing and so on. we can apply different passes that all work for any VM that you write. So the compiler code is the same. So everything goes through the same pipeline. So the main idea is that this is going to develop to maximize developer experience without actually compromising performance, which is the main thing you get by doing low-level implementations. Here's a very basic diagram of what the Powder architecture looks like. So everything you see in gray would be inside Powder or written using Powder. So we have a lot of high-level languages, C++, Go, Rust, JavaScript, Solidity, anything you want, that compile to VMs. And we can use the Powder assembly language, which is the higher-level intermediate language, to define VMs. So we can define RISC-V, which you have done, LLVM or WASM, EVM, Prolog, JVM, anything you want. And the VM itself is an input. So the VM is written in a language that is provided by this compiler, and you write the VM and then you write programs using the instructions defined in that VM. So there's nothing built in this case. At that point, you get a Powder assembly file, which can also be input back. It's compiled into our version of PIL. So PIL stands for Polynomial Data Language. It was invented by Jordi right there from Polygon. Basically, we took PIL and we changed it to fit our needs. And the PIL layer is basically a constraint language that is closer to the proof systems, and it's just constraints. There's no notion of program anymore. And here's where we do all the witness generation, some more optimizations. And at that point, you basically pick a backend, and then you just kind of further compile to that backend, and you get your zk proofs, basically. And one important aspect here is that at any point in time, at every step of the compilation pipeline, you can stop, take a look at it, everything is human readable, input back in, you can do optimizations, you can do whatever you want, use external tools, put it back in, and then continue the compilation pipeline from that point. So why exactly would you need this, or when would you need this? Maybe you don't, it's blockchain. If you are a zkVM builder, it basically enables you to write VMs, to prototype VMs, to research VMs, and get zero knowledge proofs for them much more quickly than if you had to write a VM in a circuit yourself. You can focus on the VM design, you can focus on the prover design, you can focus on prover performance, and you don't have to care about anything related to language or compiler or even writing circuits. If you just want to make proofs for existing programs, for example, if you have a Rust library that you've written already, it's been audited and so on, you just want to make proofs for your programs that use a library, you can just do it because you can simply use it as a replacement for a compiler. So instead of using Cargo or LLVM or GCC or whatever, you just use Powder, where the front end is the same, but the back end, the artifact changes from an x86 or RISC-V binary to a zk proof. So one example of front end we've been working on is the RISC-V front end. We support the RISC-V 32 IMAC subset, so it's almost complete. And it basically uses 300 lines of Powder code, which is really short for the instruction set implementation. So Powder automatically synthesizes the witness generation, constraints, and so on, and you get a zk proof at the end. And we support any Rust code that's no-std out of the box. And we're currently working on different VMs, different instruction sets. For example, EVM, Valid, and WASM at the moment. The advantage of working on RISC-V is that, for example, it's very similar. There's a lot of similar instructions and the ways things work with Valido, WASM, a lot of optimizations can be done on all of them at the same time. So it's actually even easier to build more VMs once one of them is written. And this one example of what things like, that last slide is actually old, it looks better now. So here we have actual Rust code that uses a tiny catch-ack crate. This is just a crate you can find on crates.io, and you just use it, and you use it to compute catch-ack. So this is the classic example where you're proving that you know the pre-image of a certain hash, where here, this is the hash. And this is kind of a circuit, right? So you have some public data, you have a challenge, and you're computing something in the circuit to verify that it matches whatever the challenge requires. And this compiles, you can just use Cargo and LLVM. This compiles the RISC-V code, which looks like this. It's basically AT&T assembly with the RISC-V instruction set. This is then transpiled almost one-to-one to Powder assembly code, which is on that side, which then uses the instruction set defined in Powder assembly itself. And from there, it's the same pipeline as any other program that's written in Powder assembly. So this is, for example, what Powder assembly looks like. So nothing here is built in. Everything is user-defined. So if you want to use instruction in your function, I don't know if there's a pointer here. If you want to use instruction in your function, so here, I have this add instruction, you have to define it. It's not built in. And of course, it's a library of things you can use. But the language approach requires, it's the advantage that this is an input. So we have to write it, and you can use it as a library. So here, for example, we've defined a few registers. We have a few instructions, instruction jumps. So it fully supports dynamic jumps because it's defined in the language. So you can define whatever you want, including dynamic jumps. And here, we also have the notion of a machine that's used as a coprocessor. So we have an arithmetic machine, which here is extremely simple. We just compute, we just add two numbers, x and y, we get z. And we just use it here in the main machine. And you can see here in the add instruction of the main machine, basic delegates computation to the submachine. And currently, we use a lookup to verify that this is done correctly. And the only things that are built in the language is the ability, these types basically register machines, etc., and the ability to create functions, to create registers, to create instructions, and to define labels as a start label that you see here, and to call instructions. Other than that, everything is user-defined and usable in libraries. This then compiles to PIL, which is a constraint language. You can see here that the notion of program doesn't really exist anymore. Everything is polynomials and constraints, the usual cliche. And I'm not going to go deep into this, it gets technical, but basically the execution model that we have is a table like that, where each variable is actually a column which becomes a polynomial afterwards. And we have time here as the leftmost column, and each variable gets assigned initial state, which comes from the constraints, and then from there on we execute computation, and usually the last row will be the output of your computation. And what I mentioned earlier, that some of the advantages of having a low-level way to look at things is that we can use the high-level languages and constructs to reuse code, for example, Rust crates or libraries that already exist, without losing performance. Because of course, the example that I showed earlier is a catch hack. It's going to be a massive amount of code if you compile to x86 or RISC-V. So you do want to have specialized circuits, basically, to deal with this more complicated pieces of these more complicated functions that you need that would basically be too expensive in the normal computation setup. So here we have an example of our standard library. So we have a module system as well with a standard library that is currently still pretty small, but we're always extending it. So here are the functions that we have currently in the standard library. We have, here's actually a good example that Carlos gave earlier, because we do have here Poseidon implementation for both BN and Goldilocks, because these are the fields we support. And you can basically use them in Rust. So when we go to Rust, you can basically have, sorry, this is still assembly. So you can see that we just use the module over there and then just compute things. And this is also powder assembly. And you can just use it, and this is a few test vectors, and this will use the optimized low-level coprocessor. And similarly, these are all exposed in Rust. So this is, for example, Rust test that simply uses this library that comes from the low-level powder library. And here you can see a code that basically is activated if powder is on or off, and then it uses a native version of Poseidon or the powder version of Poseidon. So you don't have to change your high-level code at all to use the level coprocessors that are more performant. And this is also, of course, extended by continuations, and you can do unbounded execution traces. And in the end, the proofs are aggregated into a single graph or flonk snark. And this enables us to do things like revm. So you literally just take revm. So here we're just importing revm, which is the Rust implementation of the EVM, and make calls to it, get some bytecode, get some data, and basically get a zkVM out of the box simply by running revm in the powder setup. Applications are, of course, many. So zk RISC-V, zk was the more obvious ones that you can run any program, basically any program in a high level. On the EVM side, we can either write a specialized or optimized zkVM written in powder, or we can use things like geth, revm, EVM1 via the other VMs. And the main advantage of all of this is that this compiler stack gives us is that all these features apply to all VMs. So it's not like it's a RISC-V implementation that has these features. It's the RISC-V and WASM and the VM and Valida and any VM. They basically benefit from every single feature that the compiler provides, meaning optimization, static analysis, form verification, possibly low-level performant coprocessor, standard library, module system, continuations. All these things are available for any VM, and the VMs are actually defined by the user. So everything is available for anything any VM that's written for any purpose might need. So yeah, thank you.